Okay, all right. Well, good morning. Happy Wednesday. Thanks for joining me online, and I appreciate your flexibility. And yeah, so here we are. And again, I appreciate anybody who is willing to have their camera on. That's always much appreciated. But yeah, let's take a look at today's lecture. So today, we are going to take a look at gradient descent, okay? So gradient descent is an optimization algorithm, and we use it to kind of find the local, local minimum for some kind of function. And so, let me just back up for a moment and and let's just take a look. So we've been looking at a few examples, and so far kind of we've been using the mean squared error as our loss function, right? So we're saying, in linear regression, what we're trying to do is we're trying to minimize this quantity, the mean squared error, right? I mean, sum of squared residuals and mean squared error are almost the same thing. They're just separated by kind of this constant. Mean squared error is you take sum of squared residuals and you divide by n. And the way we solved for it was we said, well, you know what? We want to find the W, okay? The W, the weights that will minimize the mean squared error. And so what we did was we calculated the gradient of this with respect to W. We set that gradient to equal to 0, and then we solved for W. And this loss function, it's pretty simple. It's this kind of, we call it a convex loss function, and there's just kind of a squared term. So it wasn't too hard for us to find the gradient, right? We did a lot of this in kind of matrix notation, vector notation, and it was okay. All right. Sometimes the loss function can be more complicated, and sometimes you know you might still be able to find the gradient, but setting that gradient equal to 0 and solving for W could become kind of this intractable problem, or just this like really tough problem. So maybe not impossible, but really, really tough. Okay. Sometimes it's impossible, sometimes it's just really hard. And so instead of trying to do this thing where we set it equal to 0 and solve, what we'll do is we will use a computational method. And the computational method that we will look at today is gradient descent. Okay. You took 102A, and I don't know who you took 102A with, but in your 102A class, did you cover coordinate descent? So if you took it with me, you should have covered coordinate descent. Hopefully you remember doing that in your homework assignment. But if you didn't take it with me, you still might have covered coordinate descent. And that's another optimization algorithm. It's a way for you to kind of, use computational methods to find a local minimum. Coordinate descent did it one variable at a time. You kind of held the other variables constant, and you would optimize in a univariate fashion. Gradient descent is another computational method. It's iterative. You kind of keep repeating the process, but this time you don't hold anything constant. You just you apply the gradient in this case. Okay. So yeah, so what I wrote, so when fitting our model, our goal is to find the set of parameter estimates that minimize the loss function for our observed data. What we're going to do is we treat the observed data, the data that we have, as fixed values. And the loss function is really a function of the parameters that we need to estimate. So for linear regression, we have kind of two parameters, the slope and the intercept. And we're trying to kind of, again, you're like turning these knobs and you're trying to minimize the loss function. There's actually a cool little app on the internet that I want to show you guys. This is explain visually, and let's ordinary least squares regression. So this actually has the literal knobs here. Okay, so here these are the data points, and we are trying to find the slope and intercept of the line that best fits this data. And so this one changes the intercept, and so I can turn the knob and it slides the line up. I can turn the knob and it slides the line down. And so we can see it, you know, if I put it right here, the line runs through the red and blue dots. And so we have almost no residual for red and blue, but it's kind of far away from green and yellow. So we have big residuals for green and yellow. And therefore, you know, we have, you know, big residual squared. Or I could slide the line up, and the green and yellow, it gets real close to green and yellow. And so those residuals shrink, but now it's far away from red and blue. And so those get bigger. And, you know, what we're trying to do is we're trying to find the right intercept that minimizes the total sum of squared of all of the residuals. And we can also adjust the slope of the line, right? So I can kind of keep kind of, you know, adjusting this to find, I don't know, what is the best fitting line, right? We want to minimize the total sum of squared residuals. So I have these two knobs, and I can kind of adjust those, and I can adjust the slope and try to I don't know what the best combination is going to be. All right. And that's basically what we're doing here. We're going to try to find the best combination of the intercept and the slope. Or, you know, if you have a more complicated thing, you might have more parameters, but you're just trying to find the right combination of weights to minimize the total loss, the loss function, the mean squared error, or sum of squared errors. Okay. Yeah, and then we did something called coordinate descent in 102A, and this one will look at gradient descent. So you can think of the gradient as this multivariate generalization of the derivative, right? So the derivative represents the slope of the tangent line. If you have a univariate function and you have some point x, the derivative is the slope of the tangent line at that point x. Okay. Now we are looking at this kind of multivariate function. We have a function of multiple variables. And in this case, you have some location x. It's a coordinate of several variables. And the gradient is a direction of greatest increase for the function, okay, at that location x. And the magnitude of the gradient is the rate of increase in that direction. But yeah, you're going to basically get a vector, all right, which points in the direction of greatest increase. And the idea for gradient descent is, you're on this multi-dimensional surface, right? And at your location, your current location, you find the gradient, which points uphill, okay, which points basically the direction of steepest descent. And what we will do is we go in the opposite direction. We say, okay, if that direction is uphill, I'm going to go in the opposite direction, okay? I'm going to walk away from uphill, and that means we're going to go downhill, okay? And we repeat the process. So I take a look and I say, okay, which way is uphill? I say that way is uphill. I take a step in the opposite direction, so that moves me downhill. And then after I take a step, I say, okay, now which way is uphill? And I repeat this process. So every iteration, I take a step. Every iteration I ask which way is uphill, and every iteration I take a step in the opposite direction. And I just keep repeating this over and over and over and over, and eventually I will reach the bottom. Okay, now it might just be a local minimum. Okay, but I might reach some location, some local minimum. And so when we write this out, the gradient descent algorithm, it's very, very simple. Okay, So we have some function, some multidimensional function, where you input a vector, right? So in this case, we're inputting our vector of weights. And so for linear regression, our vector of weights is just the intercept and the slope. If you have, a higher order, linear model, then you might have more terms in W. It doesn't have to be, a linear combination. It just basically it's some function where you put in multiple values, right? Some vector W, and the function spits out only one value. Okay, so it has to be multiple values in, one value out. Okay, and in our case, the one value that gets spit out is the mean squared error, right? We calculate the mean squared error. And so if we are currently at some location, we're going to say W, our current weights at time n. So our weights at time n, then at the next iteration, so our weights at time n plus 1 are going to be our current weights, W sub n, our current weights, minus, okay, gamma is just some positive scaling constant, times, and then this is nabla, okay? Nabla, or the gradient of f at our current location, W at time n. Okay, so it's just our current location minus the gradient, right? And you have some kind of scaling factor. So the gradient might be a big number, and you just say, okay, well, we're not going to do the full size of the gradient, just some, maybe 10% of it, or maybe 1% of it. Or I guess in some cases, if you end up in a shallow location where your gradient ends up being quite small, then you could have 3 times the gradient or whatever. Okay, it's just some positive scaling constant. Here I've got gamma. Sometimes in other texts you might see lambda, but it doesn't matter. Okay, so let's just try this out. Here is some arbitrary function. I've got 2 variables, x1 and x2 here. Okay, I only got x1 squared minus 2x1 minus 0.5 x1 x2 plus 2.5 x2 squared. And here I'm going to go ahead and I'm going to just use calculus to find the gradient. And so the gradient is going to be a vector of partial derivatives. And so if my input is this vector x, which consists of values x1 and x2, my gradient is going to be a vector of length 2, consisting of the partial derivative with respect to x1 and the partial derivative with respect to x2. And so if I take what is the partial derivative with respect to x1 here, I'm going to get 2x1 minus 2 minus 0.5 x2, all right? And then if I take the partial derivative of this function with respect to x2, this zeroes out, that zeroes out, and I get negative 0.5 x1 plus, and the derivative of this is going to be 5 x2. Okay, so that's going to be my gradient function. And this is what the function looks like if I plot this out. Sorry, this got cut off on the bottom, but this is in the x1 direction, and this is in the x2 direction. And we can see, okay, there's going to be a local minimum somewhere, something like this. I've got these kind of contour lines, and so you can imagine this, paraboloid shape, right? You got this kind of shape, and the bottom is going to be something like this, right? You got a bowl, and if you roll a marble, it's going to roll down to the bottom. Okay, so let's say we begin at some arbitrary location, -5, 4, right? So I think that's up here in this corner. And we say, all right, what is the gradient at that location, -5, 4? So our gradient, for the first component of the gradient is 2x1 minus 2 minus 0.5 x2. I plug in -5 for x1 and 4 for x2, okay? And so I get -10 minus 2 minus 4, minus 2, and I get -14. All right, over here, the second part of my gradient is -0.5 x1 plus 5 x2. I plug in -5, I plug in 4, and over here I get, this is 20, and this is positive 2.5, and I add those together and I get 22.5, okay? So my gradient at -5, 4 is this vector, -14 and 22.5. This is the direction of steepest ascent, okay? And so what I want to do now is I want to move in the opposite direction. So I'm going to subtract off the gradient, right? So this is a vector, okay? -14 in the x1 direction points, if I'm at this location, -5, 4, -14 points in the, to the left and 22.5 points up. So, we're getting, right, so here's my location at -5, 4, and then I'm basically, I've got this vector pointing in the direction -14, 22.5. So this is direction of steepest ascent. Okay. And okay, so what I do is I'm going to say, all right, well, I'm starting off at -5, 4. This is my current x location at time 0. And what I'm going to do is I'm going to subtract off some positive constant gamma times the gradient to get my next iteration. So here I've just chosen this arbitrary value of 0.1, okay? And so I've got -5, 4 minus 0.1 times the value of my gradient, -14, 22.5. So when I do -1 times this, I'm going to get positive 1.4 and -2.25. So now I'm kind of moving in the opposite direction here. Okay, so I'm going to add 1.4 and 2.2, -2.25. Okay. And so when I do that, I end up -5 plus 1.4 gives me -3.6. 4 minus 2.25 gives me 1.75. Okay. All right. Is that okay? And how I got this? Something like this. Okay. If I wanted to do this in R, I could do it just as easily. All right. So here I have a function of two variables, x1 and x2. This is my function for f, and it's just, x1 squared minus 2x1 minus 0.5 x1 x2 plus 2.5 x2 squared. And then my gradient is going to return, my gradient function will return a vector of two values. I don't explicitly need to write return here, but this is going to return a vector with two values. The first value is 2x1 minus 2 minus 0.5 x2. And then the second value is this -0.5 x1 plus 5x2. And so if I start off at -5, 4, I could say, hey, what is the gradient at -5, 4? And I get -14, 22.5. And then if I say, okay, take our starting location minus 0.1 times the gradient, I get exactly what I found, -3.6, 1.75, which is what we got over here. Okay, so this is just doing this in R. And so I'm going to plot this, right? So -5, 4 is right here, and then -3.6, 1.75 ends up right here. So this is one iteration. We started here, we go in the opposite direction of uphill, and we end up downhill, and this gets me closer to kind of the bottom of the hill. Okay. Let me go ahead and give you your first view quiz answer, which is the letter A. A as in apple. A as in apple is your first view quiz answer. A. Okay. Is everybody doing okay? A lot of you have your cameras off, but maybe you can give me a thumbs up reaction. All right. Okay, great. All right, I appreciate that. Let me know that you're here. All right. So, I'll accept that if whenever I say like, all right, does that make sense? Give me a thumbs up reaction. Let me know you're following along. Of course, I'd love to see your faces, but that's okay, right? It's 8:20 in the morning. It's for some of us, it's a rough start. Okay, so this was one iteration. We're now at the coordinate, 3.6 comma 1.75, or I'm sorry, negative 1.75. And then what do we do here? Okay, well, at the next iteration, we're going to say, okay, what's the gradient? The gradient is at this location is this and this. And so for the next iteration, I'm going to do take this, multiply it by gamma 0.1, and I'm going to do 3.6 minus this thing, right? So 3.6 minus 0.1 of this gives me, this is practically 10, so I'm gonna add 1 to it, so I end up at like basically negative 2.6, negative 2.5925. And here I got 1.75, and that's a little bit more than 10, and so I end up at subtract off 0.1 of that, so I end up at 0.6950. Okay, so this is where I end up after 2 iterations. So after the second iteration, I end up over here. Okay, there's my second iteration, and I just keep doing this over and over and over again. Okay, so here is a loop. I'm going to do 20 iterations of this. All right, so I'm going to start off at negative 5 comma 4, and I say for I in 1 through 20, what am I going to do? I'm going to update. So this is really it. This is all I need to do for the location. Okay, so I'm going to just take my current x vector that's going to go into row I in my locations matrix, and then I just run x vector minus gamma times the gradient, and I repeat that. Okay, and so this is the algorithm part up here, and then this is just for the plotting. Okay, the plotting is for I in 1 through 19, basically add arrows from my start location to the end location, right? Start, you need the start x coordinate, x and y coordinate, and then the end x and y coordinate. So from iteration I to iteration I plus 1, and I go from 1 through 19 here for the for this. So this part's just, this is the algorithm. Sorry, I can't write. I'm having trouble here. And this is just for plotting. Okay, so and this is what it looks like. Ta-da! And so we started off here, we go downhill, we look, and then we go downhill, go downhill, go downhill. And you can see after 20 iterations, we end up, well, we're not quite all the way at the bottom, but we end up pretty close to a local minimum. And if we let it keep running longer, we can see eventually we'll reach something very close to the local minimum. Okay, is that all right? How does that look? Feels okay? All right. Okay, if thank you for that thumbs up. We could choose a different sized gamma. Okay, so now I had chosen kind of this value of 0.1, and that's partly because I played around with it, and I knew it worked out kind of well. But you could choose a much smaller gamma. So here I've got something like gamma is 0.03, and that means our step sizes will be smaller, right? So you calculate your gradient, and rather than moving 10% of that magnitude, you only move 3% of that magnitude. So your step sizes are much smaller, and you end up, you're going to need more iterations. So this is where we are after 20 iterations, and so you would need kind of, more iterations to get to the bottom. All right, and that's fine. If you've got the computational expense or computational power, and you can spare it, you can run a small gamma and just run it for more iterations, and you'll still get there. Okay. Here's a bigger gamma. Okay, so gamma of 0.15, and so we took a big step, and we're getting pretty close to the center right there. Sometimes you end up picking a big gamma, and you end up getting kind of this weird thing that ends up happening. So here I have gamma 0.3, and remember I started off here, and it said the direction of uphill is, this is the direction uphill, and we want to go in the opposite direction, right? And here, what's happened is when we went in the opposite direction ended up, I overshot the bottom, okay? And I ended up over on this side, right? So you imagine the bowl, okay? And when we said, hey, you need to go in that direction, we took such a big step that we ended up kind of on the opposite side of the bowl, okay? And so now when I iterate, I end up kind of having to kind of go back and forth, right? So here, and we say, okay, the direction you need to go is now in this direction. But again, we took so far that we ended up on the opposite side of the bowl, okay? And so we have kind of this zigzag pattern. If you take it to the extreme, and it's a little bit hard to see, but again, if you imagine kind of this bowl, this I don't know how to draw this thing. Okay, but all right. So if we start over here and it says, okay, you need to go in this direction, and we end up over here, right? And then it says, whoops, and then you go in this direction and this direction. So this is one thing that we could end up, and we end up at the bottom. Okay. What could also happen is, let me, if I start like over here and it says, okay, you need to go in this direction. Okay. What could end up happening is I take such a big step, okay, that going in this direction, I end up, further up on the slope, okay? So I end up further up on the slope, okay, like on the valley, that I end up kind of uphill, but on the opposite side. And then so now my gradient is even steeper, and it says, okay, you need to go in the opposite direction. And my gradient is even bigger. So my step gets even bigger, and I end up on the opposite side, even farther up the hill, okay? So steps that are, way, too big can end up overshooting, can go past the center, end up on the other side of the hill, okay, or the valley, or whatever we call this, and then we end up, at a higher location, and we won't ever converge because we just keep getting bigger and bigger and bigger. So that could happen if you have a really big gamma, okay? So what do we do? How do we pick our gamma? And right now there is not a universal answer, okay? It's going to depend very much on the function you have, the data you have, and I mean the function is a result of the data you have, and the your choice of gamma is going to be heavily dependent upon that. So it feels a bit arbitrary. There's kind of a lot of trial and error as for depending on a step size. Your general recommendation is start small, like 1%, 0.001 or something, and then run some iterations, and you say, okay, does it look like it's converging? If it looks good, then you can try cranking up the gamma a little bit, run a few more iterations, check to see if it looks like it's converging, and then you keep trying there. Okay. Now this is an area of active research. There are some algorithms that kind of take this idea of gradient descent, and it tries to there's like an adaptive procedure built into the algorithm for selecting a learning rate. So there's a method called ADAM, and it tries to figure out what is this gamma value, this learning rate that's supposed to be used. Okay, but here we're starting off with just gradient descent, kind of the most basic of these things, where we just pick an alpha and we go from there. Okay, again, you're gonna see like if you do pursue, more education in statistics, data science and stuff, you'll probably encounter other algorithms that are built off of gradient descent. Kind of you start off with this basic idea of just walking downhill, and then, you might have different strategies that says, okay, this is a better way to walk downhill, right? There's gradient descent with momentum, and there's other stuff, but let's just start off here. Okay. Let's apply gradient descent to ordinary least squares regression. Okay. And so I know we keep doing OLS regression. And I like to start with OLS regression because I think it's something we understand fairly well. And so, so we'll see how gradient descent works for OLS regression. Okay, let me also give you your second view quiz answer, the letter B. Letter B today, B. B as in bear, B. All right, so for OLS regression, this is what we have. Our loss function is what we've been doing, the mean squared errors, mean squared residuals. In matrix notation, it's this T minus XW transpose times T minus XW. This gives me a 1/1 scalar value. And if we wanted to, we could find the gradient analytically, all right? And we would get the gradient of the loss function with respect to W0 to be this quantity. And the gradient of the loss function with respect to W1 is this quantity, okay? Now, I'm going to just kind of, I'll skip over this for now. In analytically, we can get the gradient, and we saw this on Friday, Monday? I don't remember when we did this. Okay, but we did this earlier, right? We said, okay, what is the gradient of the loss function with respect to W? We expanded this out. We got T transpose T, and then we said, well, those things are transposes of each other, and they're scalars, so we can combine them. So we end up with 2 W transpose X transpose T, and plus W transpose X transpose XW. And then when you take the gradient of this with respect to W, we get X transpose T and X transpose XW, or 2 X transpose XW, right? So this is what we have, -2 over n this, and 2 over n this. So this is the gradient of the loss function with respect to W. And what we'll do is we'll go ahead and we'll we can do the gradient descent algorithm either in non-matrix notation or in matrix notation. This will give us the same results, right? So we could treat this as our vector W as two parts, W0 and W1, and then we find the partial derivative with respect to W0 and the partial derivative with respect to W1, and we kind of combine them in into these vectors. Or we can just say, oh yeah, we know W at time n is these two components, and we know nabla F at time of W at time n is just this thing as well. Okay, so this is going to be our solution. So just ahead of time, I have a very, very, very small data set, 3 data points. My X values are 1, 3, and 5. And my target values are 4.8, 11.3, and 17.2. And this is going to be, this is kind of our goal values. Right, so this is, we know these are the values that minimize the mean squared error. Okay, this is the intercept, this is the slope, this we found by using ln. Okay, so these are the goal values. We know these values minimize the mean squared error. Okay. But we'll use gradient descent to try to figure this out. Okay, so this is what it looks like. These are our 3 data points, 1, and at x equals 1, x equals 3, and x equals 5. And this has an intercept of 1.8 and a slope of 3.1. Okay, so we can see this is what it looks like. All right, so what we'll do is we will code up our gradient descent algorithm. And so here, my gradient function this time is I'm going to do it in matrix notation. And so I'm going to say, I'm going to input my W vector. And we're going to say, okay, what is the gradient? The gradient is going to just be X transpose T plus X transpose XW. Now, what I have here, I'm going to take this 2n. This is just a constant, right? And so basically, what I'm going to do is I can just say I've got 2 over n times basically X transpose T plus, I'm sorry, negative X transpose T plus X transpose XW. So these are our vectors here. And so this is my nabla F. And we said, you know, in the algorithm is I've got gamma times nabla F. So what if I replace like let's say lambda with 2n over gamma, okay? Then I could just have lambda times this component. So this gradient loss function is just going to be this part. I'm not going to worry about the 2 over n inside here. It's just because I can just, it's just a constant, right? So so that's what I've got here. So when I'm going to have negative X transpose times T plus X transpose X times W. So this is my gradient function there. Okay, and then and so here the gamma, or I guess I called it lambda here, but basically this is a combination of 2 over n times the original gamma, and I'm going to just start off with 0.02, and here's my algorithm. I just say for I in 1 through 1,000, I'm not keeping track of anything. Just take your current W vector, your weight vector, and do the gradient descent algorithm. W vector minus gamma times the gradient, nabla F. Do this 10,000, or not 10,000, 1,000 times. And so after 1,000 iterations, what are the values I get? I got 1.799, 3.10, which is very close to the actual values of 1.8 and 3.1. So I got something very close to the intercept and the slope. So that's a good sign. Okay. All right. Is that okay? The code here. So again, the gradient descent algorithm just happens right in this basically 2 lines of code, the for loop along with the each iteration, right? So we did, you know, it's just basically one iteration, just or one line of code repeated 1,000 times. I want to kind of illustrate this. I hope this illustration is helpful. Okay. Shows what we're going to see is we're going to see the contour plot of the loss function and the actual kind of graph of our fitted line here. Okay. So I'm going to just start off. My starting location is intercept of -1 and slope of 1.5. Okay. And this is just code to plot the contours and plotting the path of gradient descent. So this was my path of gradient descent. It's kind of interesting. The center is down here. This is, and you can see this location right here is 1.8. That's my intercept. And my slope is 3.1. Okay. So this is the intercept over here is at 1.8 and the slope is at 3.1. That's going to be kind of my minimum right there. And we can see, you know, we started off over here you know, we go downhill and then we take a right and we kind of end up over here. So let me just kind of show you. So here, this was my starting location was intercept is -1 and the slope was 1.5. Okay. So remember my original fitted values are at X is 1, you know, 4.8, 3, 11 point something, and 5, something. So these are my actual values. And right now, if I plot a line with slope 1.5 and intercept 1, this is what it looks, intercept -1, this is what it looks like. So we've got quite a bit of, our residuals are really big, right? So so we've got a huge amount of residual here, right? So our squared residuals are these big squares, and we are way out here. So so what does the algorithm do? The algorithm says what you need to do is you need to increase the slope, okay? So now my slope is steeper. My slope is 2.312, okay? And what does that do? Well, that helps. My sum of squared errors are a lot smaller than before, okay? Because I've increased the slope, right? So I've increased the slope. I've also increased the intercept, okay? And then at the next iteration, it says, yeah, you need to keep increasing the slope. We're still not steep enough, okay? So we increase the slope more. This is after 5 iterations. And yeah, already after 5 iterations, our performance is much bigger. Our sum of squared errors is already much smaller, right? So we're taking our slope and we're increasing our slope, and that's what we are seeing over on this plot over on the left. We start off with a slope of 1.5. After 1 iteration, we're at a slope of 2.3. After a few more iterations, we're at a slope of 3.3. Okay, and after a few more iterations, we have a slope of 3.6 and an intercept of -0.23. Okay, and so, looking at this picture, what we see is, oh, you know what? Maybe my slope is a little bit too high. Okay, my slope is a little bit too high. And to kind of even out our problem, right? So these are my sum of squared residuals. Okay, my squared residuals are pretty small, but they're not we still have some values there. And if I want to shrink them, what I need to do now that I've got the slope up to here, what I need to do is I actually need to decrease the slope a little bit. And as I decrease the slope, what do I need to do? I need to kind of lift up this side. I need to lift up the intercept a little bit, right? So if you had to kind of adjust this line to kind of, try to get as close as you can to these 3 dots, what do you have to do? You want to decrease the slope, but as you decrease the slope, you need to increase your intercept. And that's what we're seeing here on the contour plot. We see in the next part, we're going, the slope is actually going to decrease a little bit, and the intercept has to keep climbing. So after a few more iterations, so here the slope decreases a little bit and the intercept goes up. And after a few more iterations, the slope decreases a little bit and the intercept goes up, right? And it takes a lot of iterations just to do this little bit of decreasing the slope a little bit and increasing the intercept. Okay, and so that gets us pretty close to where we want. And if we run a few more iterations, we'd eventually get kind of to that that local minimum where we have a where we hit the optimal values of 3.1 for the slope and intercept of 1.8. Okay. Just want to check, make sure this is okay. And the pair of plots make sense in terms of what the loss function looks like, and then what the fitted line looks like in relation to the data. Okay. Let me go ahead and give you your 3rd view quiz answer today. 3rd view quiz answer is the letter C. C as in cat. C as in cat is our 3rd view quiz answer. Okay, this is just, here's something where we ended up with too big of a gamma, okay? So, I mean, it still kind of converges and reaches the end, but again, we end up like, our step size ends up being a little bit too big, and we end up kind of bouncing back and forth on kind of the bowl here. So we have this kind of crazy zigzag pattern. If you end up with much too big of a gamma, it doesn't converge. Okay, so here I started kind of over here as different starting location. 0 for the intercept, slope of 3.5, and it just zigzags and it will not converge here. So that's a problem there. Okay. I need to talk about numeric gradient calculation, and we'll do this. Okay. So sometimes it can be tough to find the gradient. Okay. It can be tough to find the gradient via calculus. It can be tough to find the gradient via vector calculus and things like that. And sometimes you do find the gradient, but you're not 100% confident you did it correctly either. So one thing that we can do is we can estimate the gradient numerically. Okay. And so numeric gradient estimation does not require any calculus. It's a simple method. Okay. It's not efficient, but it's a simple method that works. Okay. Basically, we just add on a tiny little h, and that will give us, and we divide by h, and that will give us, an estimate of the gradient. So an important thing is you have to do each component separately. So if we have two components, an x1 and an x2, to calculate the gradient numerically, or I should say to estimate the gradient numerically, is you add on an h to the x1 and you leave the x2 alone. All right. And if you do that for one side, that will give you, your kind of approximate partial derivative with respect to x1. And then to find your approximate partial derivative with respect to x2 is you add the little piece h to x2, but you leave x1 alone. Okay. And for each time you're going to say, okay, well, how did the function change when I added h to x2? And how much did it change versus kind of my original values of x1 and x2? So let's try this out. So way earlier we calculated the gradient at my starting location of -5, 4, and we said, okay, my gradient at this location is -3.6, 1.75, right? So remember this function, x1 squared minus 2x1 minus 0.5x1 x2 and 2.5x2 squared. We say, okay, what's the gradient there? The gradient at -5, 4 is -3.6, 1.75. Okay. I'm sorry, not negative. That was not the gradient. That was the coordinate that we ended up at. The gradient at that location, the gradient at that location was -14, 22.5. And then when I combined it, I ended up over here. But the gradient was -14, 22.5, okay, on this slide. So we're going to estimate this numerically. And we're going to start off by saying, okay, what's our starting location? -5, 4. What is the value of the function at -5, 4? So I plug in -5 for x1. I plug in 4 for x2. I go through all of this. The value of the function at -5, 4 is 85. Okay, this is my current function value, 85. And then we're going to do each component, okay? Each component. So here I'm going to say, let's add 0.01. I'm going to do h is equal to 0.01. Now, oftentimes you'd probably use an even smaller h, maybe like 10 to the -5 or 10 to the -4. Again, you have to take into account floating point precision. So if you're dealing with big numbers, obviously your h can't be really small. But if you're dealing with something like 5, yeah, h of 0.01, h of probably 10 to the -5 makes sense. So anyway, I add 0.01 to this. And so now I'm going to plug in -4.99 for my x1 and 4 for my x2. We know the value of the function at -5, 4 is 85. When I plug in -4.99 into the function becomes the value 84.8601. 84.8601. And we say, okay, well, that's a difference of -0.1399. And if I divide by 0.01, that becomes -13.9. For the x2 component, the partial derivative with respect to x2, I add 0.01 to x2. So I'm going to plug in 4.01 over here. And I say, okay, what's the value of my function if I plug in 4.01, right? So basically I plug 4.01 in for x2. and you get 85.225, okay? All right, how much did that change? It changed by around 22.525, okay? And so my numeric estimate of the gradient is negative 13.99, comma 22.525. And that's pretty close to, again, if I go all the way back to slide 10, you know, the analytic gradient is negative 1422.5, okay? But here we didn't do any calculus. All I did was just some computations by, you know, adding a tiny little h, in this case 0.01, to the component x1, and then 0.01 to the component x2, okay? The important thing is that you do these things separately, okay? You do x1 over here, you leave the x2 alone. You add 0.01 to x2, but you leave the x1 alone. And so you're going to get two separate components, and that will form your gradient. Okay, we will end here for today. Sorry for going a couple minutes over, but we'll go ahead and end here, and we will see you on Friday. Have a good night, or have a good day.